Hi class, and welcome to our guided notes section on Skill 4 from Unit 4, which will be on graphing the square root function, which is one out of our two parent functions for this unit. So hope you enjoy. In this video, we're going to look at graphing what's called the square root function. That's a function that looks like this right here, where y is equal to the square root of x. This is what we call the parent function. Because basically the parent function is when a is 1 and h and k are 0, meaning there's just a 1 being multiplied outside of the square root and then nothing is being added or subtracted to x either inside or outside of the square root, because eventually we're going to be looking at things where a may not be 1 and something might be added or subtracted to x on the inside and then also on the outside of the square root. But before we get to those, we like to go back to the parent function where it's just plain and simply square rooting just the x. So because we are square rooting numbers, you may notice over here I have only chosen 0 and then positive numbers after 0 to plug into the square root, because when we're working with functions we only want real numbers in our domain and range, so I don't want to have to square root a negative because that would lead to an imaginary number. But I didn't just choose any positive number. I chose numbers that are easy to take the square root of, right? Because I want to just get some nice, easy points to look at my graph down here to talk about some of the defining characteristics. So I'm plugging in numbers that are perfect squares. And then the y value is just going to take the square roots of those numbers. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So 0, 1, 4, and 9 are my x's for my parent graph, and then 0, 1, 2, and 3 are my y values for my parent graph. Now you might be wondering, Mrs. Lasner, why didn't you take the positive and negative square root, right? Back when we were solving quadratic equations where we had x squared and we would square root both sides, I made you write plus or minus in front of your square root sides. And so the answer is sort of given to you in this little text box over here to the right. So it has to do with making sure this equation is a function. So if you recall, any non-negative, right, positive, any positive real number will have two square roots. That is true. It'll have a positive root and a negative root. Okay, so I just chose 9 as an example. You could say that both 3 and also negative 3 are considered square roots of 9, since both of them, if you squared them, would equal 9. But there's another name we call the positive square root. It's also known as the principal root. And whenever we want you to take only the positive root, we indicate that with just a positive square root sign. It's understood, okay, that when you see just the positive square root sign like this, that it's only referring to the principal root, which is the positive root, okay? So when you see square root of 9 written this way, we understand it's only referring to 3. If we want to talk about the negative square root, we call it that, the negative square root of 9, and then that would refer to negative 3. If we want to talk about both roots, we use the plus or minus sign. The positive and negative square root of 9 would give us both positive and negative 3. But if all you're looking at is a plain square root sign, then we need to understand that that is only referring to the positive root, which is the principal root. So when we look at this equation, y equals the square root of x, we understand that we are only taking principal square roots of x for every single one of them. So we're only taking the positive square roots of x for every single x that we plug in here. Okay, so my y values are only ever going to be positive, as are my x values in this function. In this square root function, we are using these understandings that we're only going to take the principal root, and we're only going to even plug in positive numbers to begin with. So let's plot those points and see what happens. So this would be the point 0, 0. This would be 1, 1. This would be 4, 2, and 9, 3. So those are my points, and when I connect them, it kind of makes this slow and subtle curve. It is increasing, okay, as the x values get bigger, their square roots will get bigger as well. It's not increasing very quickly, but it is increasing. Now, before we go on to talk about all the defining characteristics, I want us to pause for a moment and consider the relationship between the square root of x and x squared. It's an important one for us to understand. So it may help for us to revisit this parent function, the x squared parent function. This is from Unit 2A. Okay, so we're back in middle of first semester now. You may recall at that time, I was using -2, -1, 0, 1, and 2 as my inputs, as my x values. And then for the y values, I was just squaring those. So my y values were all coming out positive. So I had 4, 1, 0, 1, and 4 as my y values. I think I'm going to just add one more point, though, just to help compare it a little bit to the parent function over here. So these were the points we used for the parent function. And then when you graphed them, as you recall, it formed a parabola, or it looks like a U. It kind of goes like this. Okay. So this was our parent function for y equals x squared, and it was a function, right? It passed the vertical line test. You may notice, though, it's not a one-to-one function. It fails the horizontal line test. Okay, so that's going to become important in about a second. So then, if you look at these ordered pairs, so I want you to focus on just this part of the table. Okay, just this part of the parent function for x squared. We're going to look at 0, 0, 1, 1, 2, 4, and 3, 9. And I want you to compare that to my parent table for the square root of x function. I want you to notice the ordered pairs are the reverse order. Of course, 0, 0, 1, and 1 are the same because the x and y were the same, but 2 and 4 switched to become 4 and 2. 3 and 9 switched to become 9 and 3. And I want you to think about the the lesson we just went over on inverse functions, and how an inverse function basically just reverses the order of the ordered pairs from the original function. So what I want you to notice is the square root of function is the inverse of the x squared function. So I'm going to plot it again over here. I've got this point, that point, 4, 2, and 9, 3. You may notice how it has that y equals x symmetry that we were talking about as well when we were graphing inverse functions. Although you might be wondering, but Ms. Lasner, it's only showing like half. It's only showing half. Okay, and I would say yes, you are correct. That has to do with this whole principal root thing because I'm only taking the positive square root. But let's suppose I did take also the negative square root. And so when I thought about the square root of 9, I allowed it to be both positive and negative 3. Well, that would give me a point here. And if I took the square root of 4 and got both positive 2 and negative 2, that would be here. Square root of 1, both positive and negative, that would be there. So if I allowed myself to take both of the square roots that I know there are, positive and negative, then I would see, oh, look at that. It's the exact 100% inverse of y equals x squared. But remember earlier we were saying y equals x squared is not a one-to-one function. It breaks the horizontal line test. There's two different inputs for the same output. So when I switch input and output and reverse it to be 0, 0, 1, 1, 4, 2, 9, 3, well then that is going to break the vertical line test, and that is much more serious. That means there's now two outputs for the same input. If I plug in an x, I'd get two different y values, and that's not even a function, let alone one-to-one, right? That's bad. So what was decided was that, okay, if we take off the bottom half, if we basically take off the bottom half and only use the top half of the square root, in other words, we only use the principal root, right? We take off the negative. We only use what's called the principal root or the positive root. We don't do the negative root. Then we can, it's kind of like we can just take the inverse of half of the parabola. It's almost like we chop off this part. Sorry. we chop off half of the parabola, right? This, and this. And then the bottom half of the other parabola, right? Take that all off. And then what do you know? Now you've got things that are exact inverses of each other. And this original function is now 1-to-1, and the inverse is now a function, and they're exact inverses of each other. So we could kind of say this. Let me clarify this a little bit. We could say they're inverses of each other. Inverses of each other when or for values of x that are greater than or equal to 0. So from here on, x squared and the square root of x are exact inverses of each other. And that's how I want you to always think of it. They will basically reverse each other. The square root will undo the square will undo the square root, and they will act as inverses of each other. But I also want you to keep in mind that the square root is basically just the top half of what would have been a sideways parabola, okay? Now I have a little name for this graph. I like to name all of my graphs. This one I refer to as the eyebrow. So when we're in class and we're practicing these, I'll go, okay, don't forget about the eyebrow. So you can kind of remember it has a starting point, and then it just kind of sort of goes up like this, sort of like an eyebrow. It goes in one direction, has a little bit of an arch to it. Anyway, that's the general shape, but it's the top half of what would have been a sideways parabola. It's the positive square root, not the negative square root. That's what the bottom half would have been, by the way. Bottom half would have been the negative square root. So we just take away the negative part and only use the positive part, and it makes a graph that looks like an eyebrow. So for the characteristics, let's go down to that now. Now we're just looking at the top half, okay? So the domain is only for positive x's. That's just so we can keep our values to be real numbers versus imaginary. Now to keep the graph a function, we only take the top half of the eyebrow. So our range will also only be positives. That's to make sure that our equation is a function. Both the x and the y intercepts for the parent function are at the origin. They both start at 0, 0. The parent function is increasing from the x value of 0 moving toward infinity. On that interval, the graph increases. The graph of the parent function never decreases and therefore does not have a max, right? Because it never turns around and goes back down, so it just keeps going up forever. But it does have a low point, a minimum point when the y value is 0. Okay, and that happens at the origin when x is 0. So 0 is the lowest value that a square root can have since we're not allowing the y values to be negative. And these graphs are 1-to-1 because we chopped off the bottom half, so now it passes the vertical line test, and then it was already passing the horizontal line test, so yes, it is 1-to-1. So that's the parent. That's plain y equals square root x with a equals 1 and h and k are 0. But what we're about to graph are scenarios where we may have an a value that's not 1, okay, and an h and k value that aren't 0. So as a quick reminder, these are the things that the a value will do to the graph. It will either reflect, stretch, or compress. It reflects if a is negative. It stretches when the absolute value of a is bigger than 1, so numbers like 2, 3, and beyond. It compresses the graph when the absolute value of a is less than 1. Numbers like 1/2, 1/3, so on. Okay, so that's what a does, and that is because a is multiplying to the y value. All right, so that's why it has such an effect, reflecting, stretching, compressing. And then the h value will horizontally shift, right? It will move the graph right or left, and it's always opposite of what you might think, and that's because of the negative in the general equation. H is coming after a negative. So when you see x minus 5, h is just the 5. It's positive. If you see x plus 5, that must have meant that I had subtracted a negative 5, and therefore h is negative. So h is always opposite what we think. Okay, and then the k value vertically shifts the graph either up or down. It's very straightforward. The signs are exactly what you see. So this adds to the x value. And something that might help is it will be under the radical sign. in these scenarios. H will be whatever is under the radical sign with x. K adds to the y value. So that's the effect that they have on the graph. Now here's how we will make the graph. We'll identify the parent function, which for this particular skill is the square root of x. We'll make a table of values for the parent function, which again for this particular parent function will be positive perfect squares, right? 0, 1, 4, 9, and then their square roots, 0, 1, 2, 3. We will then figure out what the transformations are going to be, and then any h values will add to x. A will multiply to y, and k will add to y. Then we'll graph our new points and then determine all the characteristics from there. So let's try a few on the back. So in example 1, part A, we have a very straightforward square root graph here. The a value is still 1. Okay, there's no number being multiplied out in front, so a is 1. The h value, if you're paying attention and not getting confused by the plus, is actually negative 2. It's opposite, right? And it has to do with the 2 because h is whatever's inside the radical, whatever's under the radical with x. And then k is negative 5 because that's the number adding after the radical, or subtracting, I should say. It's outside the radical, so it's the k value. So I'm going to make my table of values, and I'm going to start with the parent function values, which were x, and then y equals the square root of x. And that was 0, 1, 4, and 9. And then the square roots of those numbers were 0, 1, 2, and 3. I start with that. But then from there, in this case, I'm going to subtract 2 because that was my h from all of my x's. Okay, a was 1, so I don't need to worry about that. K was negative 5 though, so I will need to subtract 5 from all of my y values. Okay, and so this will equal, these will be the points, negative 2, negative 5, negative 1, negative 4, 2, negative 3, and 7, negative 2. That's what I get when I do all of these things. And so these are the points that I will plot. So negative 2, negative 5, negative 1, negative 4, 2, negative 3, and 7, negative 2. So there's my eyebrow, right? It doesn't go all the way around to make a sideways parabola, but it's just sort of like the top half, and it just starts right there at negative 2, negative 5. So we're going to think of HK. So HK won't really be our middle anymore. It's going to be our starting point now. It's going to be like this starting point on the graph, negative 2, negative 5. That's our HK. Okay, so that's what you want to look for in your graphs. The first point, not the middle point, but the first point should be our HK from our equation. And there's our graph. Okay. Now let's try another one over here. We've got example 1b. This time, though, I do notice an a value. So I've got a is equal to negative 3. I've got h is equal to negative 1 because there was a plus 1 under the square root sign with x. And then k is equal to 0 because there was nothing being added or subtracted outside of the square root. So I begin, of course, with my parent function where I was just doing a plain square root of x. And then I remember what those are. So it was 0, 1, 4, and 9. Positive perfect squares. And then their square roots, 0, 1, 2, and 3. Then I recognize that h is negative 1, so I need to subtract 1 from my x's. And a was negative 3 being multiplied to the y value, so I need to multiply all of my y values by negative 3. So that's going to cause a vertical reflection as well. Okay, so the points that result from that are going to be negative 1, 0, which is my HK, right? Should be my HK. And then 0, negative 3, 3, negative 6, and 8, negative 9. Okay, these are my points to plot. So negative 1, 0 is right here. 0, negative 3, 1, 2, 3 is right there. 3, negative 6, 1, 2, 3, 1, 2, 3, 4, 5, 6 is right there. 8, negative 9, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, kind of like right there. So this is, here we go, let's look at this. So this is the bottom half, right? This is the bottom half of a sideways parabola. That would have been a lot wider if you can picture this, right? This dotted part is not part of my answer, but I just want you to see it. It's still part of a sideways parabola, but it's a lot wider because it's had a vertical stretch, okay? This has had a vertical stretch because the A value, the absolute value of it was 3. But it's also had a vertical reflection because the A value was negative, which is causing the typical eyebrow, right, the top half of the parabola, to flip over and reflect over the x-axis, giving me the bottom half of the parabola. So see, when there's a negative in front, that tells me, okay, now I'm taking the negative root, right? But I've got to have that negative in front, and I'm only going to take the negative root now, okay, just the bottom half. So positive square roots give you the top half of a sideways parabola. Negative square roots give you the bottom half of a sideways parabola. And if the A value is bigger than 1, it's going to really stretch it down. So now these are more like bags under the eyes, right? The top half is the eyebrow. The bottom half would be like the bags under the eyes. Okay, why don't you guys try a few? Flip to the back page and just try graphing a few. Pause your video here, try it out, and come back when you're done. Okay, so here's the answers I have for my 2 graphs. For the first one, the first you try, there's a vertical stretch going on, so it should be a little bit higher, like a raised eyebrow, okay? It has shifted to the right 3 because H is 3, and then down 4 because K is negative 4. So the starting point, right, the starting point is at HK, 3, negative 4. And so here's my table here, and these were the points I had: 3, negative 4, 4, negative 2, 7, 0, 12, 2. I didn't actually graph 12, 2 because it was way off my grid, but I was able to get a good enough picture of the graph with these 3 points, so that's what I chose to plot, and then there's the picture of the graph. In the second one, well, actually it might help if you rewrite this equation to have the negative square root of x first and then plus 2. Then it's probably more obvious that A is actually negative. There is no H because nothing's added to x under the radical sign, and K is actually positive because it was coming before the subtraction, not after. So here's my table. The x's didn't change because H was 0, so there's 0, 1, 4, 9, the positive perfect squares. And my y values, I took their square roots, right, 0, 1, 2, 3, and then I multiplied all of those by A, the negative 1, and then added K, added 2. And so I got the point 0, 2, 1, 1, 4, 0, 9, negative 1. And I was able to plot all those. The 9, negative 1 went off the grid a little bit, but not too much where I couldn't fit it on or fit it in the graph. So it's a regular sort of eyebrow, but it's not the eyebrow, it's the bags under the eyes or the bottom half of the parabola because we're looking at the negative square root, right? So it's the bottom half of a sideways parabola that's been shifted up 2. And that's it for this video. In the next video, we'll go and take a look at all of the defining characteristics like domain, range, intercepts, all of that. That's coming. But for now, I just want you to get a hang of this graph and graphing it, and so I'll see you in class for some practice.